Hi, guys. Today we are going to finish off 6.2, the cardiac cycle. So it's technically E and F. E covers blood flow through the heart, and then F is going to cover the electrical impulse and timing and pressure that happens during that cycle. Okay. So doesn't that look kind of gross? But yeah, that's the heart. It's a beating heart. And we're going to talk about how that whole thing happens. Now, if you look, just like looking at the heartbeat for a second, you can kind of tell just a couple of things. It doesn't squeeze everywhere at the same time, right? You actually have waves of contractions that happen. You can see the atriums up on top squeeze and then followed by the ventricles and they squeeze up. And we'll talk all about that in just a minute. But if you look, it's not just like the whole thing squishes in. You can see it's almost like a wave from top to bottom and then bottom up. Okay, so just as a refresher, the cardiac cycle refers to a complete heartbeat from beginning to end. Blood passing through vessels and chambers results in circulation in the body, right? And that was William Harvey who discovered that blood actually isn't consumed by your organs. It goes back towards the heart through your veins. He banded off his arm, right? And his veins popped out and he said, "Hey, if I'm cutting off circulation and I can see a vein bulging, that means that blood is trying to leave this area and go back to the heart." And he could prove circulation that way. The force of blood pushing against the walls of your blood vessels is known as blood pressure. And the number of heartbeats per minute is known as heart rate. So, blood pressure is the actual force of blood pushing against the arterial walls or artery walls. And the number of heartbeats per minute is known as heart rate. So, the cardiac cycle has two major phases, systole and diastole. And these are also the two numbers that you hear when you hear about your blood pressure. Like if your blood pressure is, you know, 120 over 80. My blood pressure tends to be right around between 100 and 110 over 70, which is pretty low. Other people, it's a little bit higher. Systole is the phase of the heartbeat when the heart muscle contracts and pumps blood from the chambers into the arteries. So that's rising pressure. And we say from the chambers, we're really talking about the ventricles, right? Into the arteries, right? So from the ventricle into the artery. And that's rising pressure. You can see how that would be rising pressure because the ventricles are pushing in. It's like a V pushing in. And you can see down here, right? So here's this V, and as it pushes this way, that's going to increase blood pressure in these blood vessels because you're pushing a lot of blood into them. You're increasing the pressure. Diastole is the phase of the heartbeat when the heart muscle relaxes and it allows the chambers to fill with blood. So as the heart muscle relaxes, right, it kind of relaxes and gets bigger and blood fills the heart and then the heart contracts, squeeze and pushes it out. And that's when you have high pressure. So you've got two major phases, systole, higher pressure, right? And that's when the blood is pumping or the heart is pumping blood out. You've got diastole, which is low pressure, and that's when blood is coming into the heart. It's filling. It's like filling a balloon. It's like water cascading in, low pressure. Okay. So, application 2, pressure changes in the left atrium and left ventricle and aorta during the cardiac cycle. So, we're going to do the entire cardiac cycle, and the understandings and applications and skills are going to fall right in with that. So, just make sure you're paying attention to both. So, during systole or systole, same thing, systole, the first part is called atrial systole. And this is when the atrium contracts beginning on the right side, left atrium, right? Pushing the blood through the atrioventricular valve, filling the ventricles. 2 is isovolumetric contraction. So isovolumetric, iso means equal, volumetric is volume, a measure of volume, contraction. So what that means is that if you see isovolumetric, that means no change in volume. Isovolumetric, no change in volume. So this is when the ventricles contract, but there's no volume change because the valves are closed. So that's you have this V and it's starting to push in, but because these valves are closed, There's no change in the volume. So it's basically just pushing the blood closer to the door. But there's no way for it to get out because remember, our blood's going to come in and go out this way. Our blood's going to come in and go out that way. So here, let me do that again. Okay. So number one, let's back up. Number one, atrial systole or systole is when the atriums up here, these guys, they contract. They push in. And that's going to push blood down into the ventricles. Right? 2 is this isovolumetric contraction. So now the ventricles are going to start pushing in, and that's going to push blood up towards these valves right here. But isovolumetric, no change in volume, meaning no blood is leaving because those valves are shut. Okay. 3, rapid ejection. These semilunar valves, they open up, and that's when blood really gets pushed out. So that's pretty high pressure. Okay, so 3 is really the thing about 3 is you've got those valves opening up. So 1, I know I keep repeating myself, but this is a complicated cycle, and I just want to make sure we're clear. 1, atriums push down. 2, ventricles push up, but nothing can happen because the doors are closed. 3, those doors open and blood gets pushed out, right? And remember, this is systole, so this is high pressure because you actually have contractions going on. So these are contractions of the heart. It's when the heart is squeezing together. Oh, and there's 4, which is reduced ejection. So there's a decline in the pressure and blood flow because most of it's exited already. So it's kind of like the last little push to get everything out, but it's less pressure because there's not as much blood left over. Most of the blood goes through through the blood vessels in 3. So this is where most of your blood gets pushed out, and then this is just kind of like getting the drippy stuff out. Okay, now let's talk about diastole. And now this is when the heart is relaxed. Okay. You've got isovolumetric relaxation. Isovolumetric, no change in volume, meaning no blood coming in or out. Well, there's a little coming in, but you're not changing the pressure very much. The chambers of the heart relax, everything kind of sags and releases, and then blood is going to passively flow into the atria. So it's going to come in. It's just kind of like dribbling in. It's not pushing really hard. It's just kind of passively flowing into this first chamber. Then you have rapid ventricular filling, and that's when the mitral valve on this side, so this is actually the mitral valve here, valve opens and the left ventricle fills rapidly. So this guy fills all the way up. And then you have diastasis, and that's the initial passive filling of the this side is all passive. So this is like passively filling the whole time. This is like pressurized pushing it in. So diastasis is really when you've got this side filling up. And this is the last stage before the whole cycle repeats. So really, the left side fills faster than the right side. So you've got isovolumetric relaxation. That's when the heart relaxes. You've got a little bit of blood that's passively filling into both the atrium, just a little bit. Right? So you've got just a little bit that's passing, that's filling this up. And you have a little bit that's filling this up, right? Then 6, the mitral valve, this valve opens up and this valve opens with force and this blood rapidly fills up and you fill up most of the space. I don't know if you notice this, but like the muscle width on this side is much thicker than it is on the other side. And then diastasis is the passive filling on the other side, right? And then after this, you go back into systole And that's when your atriums start to contract. They're pushing that blood down forcefully, and then it gets pushed back up and out. So that's kind of messy and it's kind of all over the place. And I'm going to go through that a million different ways, a million different times to make sure that it is more clear because you're going to get tested on it. So, as a review, let's see, make sure I have my colors. It says use blue to show the flow of deoxygenated blood through the heart. All right, let's do blue. All right, so blue is going to go through. And remember, let's just do our left and right. This looks like it's left, so it's actually right, right? And this looks like it's right, so it's actually left. And you've got your deoxygenated blood on the right side and your oxygenated blood on the left side. All right, so let's do, we've got passive filling during diastasis. And this blood kind of fills up here. And then we've got passive blood flowing into the atria here, right? And then this mitral valve opens up and this fills up all the way. And we've also got some filling over here, but it's a little passive. Pressure on this side is always a little bit lower. The urgency is to get your oxygenated blood out to tissues, not so much to get the deoxygenated blood to your lungs, right? So most of the important musculature is on the left side. And then we're going to have that atrial, during systole, we're going to have the atrial contraction. It's going to start pushing blood forcefully in and on the other side. And then we have the isovolumetric where it's pushing up towards the gate, but this is actually closed and it can't really go anywhere yet. And then we have rapid ejection out. And let's do the same thing on the other side. Out. And this stuff's going to the lungs, right? No. This stuff's going to the body, right? This stuff's coming from the body. And this stuff's coming from the lungs. My writing is horrible, but that's okay. Yours will be neater. Okay, so just a structural review of the heart and the four chambers. Now let's start talking about how this process actually happens, because this process is actually not strictly controlled by your brain. Now, your brain stem, right, the part of your brain that's actually like in the back of your neck, just below your skull. So if you put your hand behind your head at the top of your neck, you'll feel there's like a little dent right at the base of your neck, right there. That's your brainstem. You'll notice that cats, when they hunt, or other predatory animals, when they grab something, they always grab it by the back of the neck. That's because they're trying to pierce the brainstem. It's the fastest way to kill an organism, or they grab it by the front to suffocate them. But that's because your brainstem is back there in the back of your neck. And that does play some role in regulating respiration and heartbeat. However, it's not the only part, it's not the only thing that regulates your heartbeat. Oh, there we have a heart. See? Oh, what's he doing to it? Nothing. Okay, good. I forgot that I put that in there. Yep, there it is. Look at all that fat. All that fat. This person has got, you can't even see the coronary arteries. This person's got some issues. Besides the fact that there's like pipes everywhere. I got some fatty issues. All right. So, understanding number 8, the heartbeat is actually initiated by a group of specialized muscle cells in the right atrium called the sinoatrial node. So there's actually electrical cells in the heart that act as a pacemaker for the heart itself. So independent of stimulus from the brain, or independent of initiation by the brain, your heart has electrical conductivity without nerve cells, which is crazy, right? The sinoatrial node is made of smooth muscle. We should probably put it in there. Let's fix that. No, we can get rid of those. Let's see. Smooth. Smooth muscle cells that initiate the heartbeat without neurons. And that ability is called myogenic, meaning like they can initiate impulses themselves. Myogenic. So within the own space, it can initiate its cells. And I like this diagram too because it actually shows you the blood flow. So here you can see blood filling in, and then getting pushed out. So, and you can see that sinoatrial node is right here. And we've actually mapped out exactly the paths of the nerves and how it happens. And that's helped us figure out kind of the actual phases of the heartbeat. You can see it actually does occur like a wave from the top down, top, bottom, up, right? So, understanding number 10, the sinoatrial node sends out an electrical signal that stimulates contraction as it's propagated through the walls of the atria and then the walls of the ventricle. So, like I said, it's top down. It starts at the top and works its way down. I'm like touching the screen with my finger and I keep forgetting that you can't see me, but yeah, starts at the top, works its way down. Why is that out of order? There it is. Okay. So first, the sinoatrial node contracts and it sends a signal that spreads through the atria, causing them to contract. And then two, the atrioventricular, the AV node receives the signal and passes it to the ventricle. So here we have one, right? Passes it to the atrioventricular. You know, it's in between the atria and the ventricular because it's got both words in there, atria ventricular, right? So that signal gets passed here. And then three, ventricles contract as the signal passes, pushing blood into the artery. So that signal is going to come down this way and it's triggering the ventricle to contract. So three. Now, you've all seen a heartbeat sign at like the doctor's before, right? And you can see it down here. So here you can see what's going on in the heart and the different bumps in the waves, right? Because your heartbeat is it in like if you think about it, it's not just thud, thud, thud. There's like two thunks. It's like the thunk, the thunk, the thunk. Like the little thunk is the atria contracting. The big thunk is the ventricles contracting, right? So here we have, you can see atria contracting. And then here, you can see this is the ventricles contracting here. So this is the atria contracting. And then this big spike is the ventricles. And then you can see the atria filling again. So that thunk, it does have two actual beats. And that's because the sinoatrial node initiates the contraction and it takes a second or two to get from top to bottom. So you get that thunk on top and the big thunk on the bottom. So understanding 11, heart rate can be increased or decreased by impulses brought to the heart through two nerves from the medulla of the brain. So, like I said, here's the brainstem in the back, right? So, whenever you see something that's like a predator and they have big teeth, they're always like going after this part of the brain because they're trying to stop your heartbeat. Now, the vagus nerve, this is one of them. The vagus nerve is parasympathetic. So you have the autonomic nervous system, which is like you consciously moving your hand. Like you look at your hand and you say, I want to pick up a pencil. So you tell your hand to pick up a pencil. That's the autonomic nervous system. And then you have the sympathetic nervous system. And the sympathetic is below consciousness. So like reflexes, like when you bang your knee and your reflexes hit, or breathing, or your heart beating, all this stuff that your body does on its own without you thinking about it, that's the sympathetic nervous system. So heartbeat falls under sympathetic or parasympathetic. And the vagus nerve, part of it actually runs through your forehead, which is kind of cool. It's also like you can smack the vagus nerve to keep yourself from sneezing sometimes. Not all the time, but. So, okay, let me get back on track. Heart rate, right. Sinoatrial node contracts in response to the signals it receives from the brain. So, like I said, the initiation of the contraction of the heart starts in the heart, and that ability is myogenic. Now, that doesn't mean your brain doesn't play any role. It does influence cardiovascular rates, and that ability is centered in the medulla. And then once that medulla sends the signal either through the vagus nerve or through the parasympathetic or the sympathetic cardiac nerves, that can increase the rate of heart rate or decrease. So decrease would be like sleeping. That's going to be the sympathetic cardiac nerves and vagus nerve. I can't remember if that's flight or fight. That's usually like an increase. I'm pretty sure. Yeah, one signal increases the heart rate while the other signals decrease. I think it's vagus nerve is increase and sympathetic is decrease, but I could be wrong about that. And also, your heart rate can also be changed or influenced by the brain in response to things like blood pressure. So, a lot of times you think of like your heart being the thing that's driving your blood pressure because your heart is the thing that's pushing your blood around. But remember, those arteries, they have those thick walls. So if your brain is telling the arteries in your body and the arterioles to relax, right? That lumen's going to get bigger. If it's telling your everything to constrict, like when you have a lot of caffeine, right? Vasoconstrictor. Is caffeine a vasoconstrictor or a vasodilator? Dilator means to open, constrict means to constrict. Anyway, you can take all sorts of different chemicals in your body that cause these arteries to either shrink the diameter of the lumen or increase the diameter of the lumen. And that has nothing to do with your heartbeat. So your heart actually changes in response to your blood pressure. So your heartbeat can change in response to that. Also, oxygen concentration, right? If your oxygen concentration in the body is low, you probably have a high carbon dioxide content and you need that switched. So your heart will speed up trying to push more blood to the lungs to get that exchange happening. And then pH as well. So pH can actually change if you go into something like cardiac acidosis or, oh, I can't remember the name. It's when your blood gets too acidic. It's something acidosis. Where your blood gets too acidic, it can change your heart rate. Because remember, your heart is the thing that's pushing your blood where it needs to go to help maintain homeostasis throughout your entire body, whether that's delivery of something like glucose, whether that's something like controlling the amount of carbon dioxide or oxygen in the blood by getting blood to the lungs or to the brain, or you've got different pHs going on. You've got acidosis is actually usually caused by too much carbon dioxide. Your heart is the thing that's pushing the delivery system. So changes in heartbeat are expected when those homeostatic conditions in the body change. Your heart is helping to maintain homeostasis by making sure everything's happening at the proper time. Okay, so I just babbled a whole lot. So, in addition, there's stuff called epinephrine. You probably heard of norepinephrine and epinephrine before. These can also change heart rate. Now, this is a hormone. Hormones, I believe, are proteins. Steroids, right? Hormones and steroids are proteins. So, epinephrine, otherwise known as adrenaline, is secreted by the adrenal glands when this is what initiates your flight or fight uh, for vigorous physical activity, right? So when your heart starts pumping really fast because something bad's happening, that's a result of epinephrine. And that's a good example of a hormone changing homeostatic conditions in the body and increasing your heart rate. Now, remember, that is a signal that is not sent by the brain. This is a chemical messenger that's being sent by your body to change heart rate in a response to maintain homeostasis when you need higher oxygen concentration in your muscles. I want to say there was another one too. Um, Crap, the stuff that they give your heart when you overdose. It's like adrenaline. Norepinephrine. No, it's not norepinephrine. Sometimes you get straight epinephrine to the heart, and that'll jumpstart your heart. So when you see like in Pulp Fiction where John Travolta stabs Uma Thurman in the heart with the hypodermic because she overdoses, it's to get her heart beating again, right? It's to initiate that heart rate. Okay, so that was a bunch of information that I went through. It kind of summarized um, the stuff you need to know. Now, I would like for you to spend some time watching this cycle happen, and I want you to create kind of your own one pager on the cardiac cycle. I know you're probably taking your notes, and you can do this right in your notes if you want. That's fine. But for your test coming up, not you're going to take a quiz in a few minutes on this particular stuff, but on your test, this particular assignment will be very helpful. So you're going to click on that link, and that link is in the assignment for you. You may have to enable Flash, a big box. It might come up just like blank where it says, enable Flash. And if you just click enable it, it'll show up. So here you have the heart, and here you have the atria up here, and you have the ventricles down here. And check it out. You've got systole, atrial systole, isovolumetric contraction, rapid ejection, reduced ejection, isovolumetric relaxation, rapid ventricular filling, and diastasis. We wrote about all these in our notes. So here they all are. Over here, you have a graph. This graph is extremely important. You will see it on tests, and it's going to ask you what's happening during different phases. So the green line, for those of you that are colorblind, I'm sorry, it's the top one up here, right? I didn't make this. I'm borrowing it from somewhere. Anyway, this line up here, this line is aortic pressure. This is a pressure graph, pressure over time, right? The red line, which is this big one here, that's pressure in the ventricles. This little orange line here, where it says ACV, that's the pressure in the atrium, and then the vent volume. So don't worry about the vent volume so much. And then down here you have an electrocardiogram. So this is what you would think of when you hear of like a regular heartbeat, like in the hospital. Here's the big thud, and here's a little thud, and then here's the actual sound. So you can see the little thud is a little bit after, but the big thud is the ventricle contraction. So if you go to here and click on these, I don't believe these links work anymore, but they're basically the same thing that's in our notes. The whole point of this simulation is that, watch this. Oh, there. So you can see what's happening and exactly how long it takes. You can see where the blood is going. You can see what phase it's in. You can find out exactly how long each phase takes, which is important. I know that there are questions that are going to ask you, how long do certain valves stay open, right? Tell me what the pressure is during certain phases. So your job is to create an annotated diagram that's explaining exactly what's happening at each one of these stages, right? Including the time and the pressure and the different parts of the heart. Now, however you want to do that is fine with me. But the more information that you can fit into what's going on, the better. Okay. And then additionally, this is the page you're on right now. The video is not embedded yet because I'm making it right now. There's also another YouTube video. This video is about 8 minutes long. It's by another guy that actually does this pretty well, just in case I wasn't as succinct as I needed to be. So there's the simulator link. This is the other YouTube video. It's about 8 minutes long. And then you have a series of questions to answer using that nice little one pager that you just made. So enjoy the rest of the cardiac cycle. I'm looking forward to seeing you. I should be talking to you about your IA stuff right now. So yeah, have fun. If you have any questions, as always, send me an email. Let me know what's going on. Okay. Or send me a reminder. It's probably faster. Bye, guys.